Okay, today we are going to talk about the free symmetric top. Let me try to sketch such an object. Let's say this top is fixed at this point here, and that this is equal to the reference point. Then we choose as the body fixed frame, we choose, as we had done before, we choose the eigenbasis of the moment of inertia of this symmetric top. So let me try to indicate that. So let's say this is the body fixed frame, and let's call these axes E1 prime, E2 prime, and E3 prime. Now I assume that the top is symmetric, meaning that it's symmetric around the axis spanned by basis vector E3 prime. So we assume that this axis here is a symmetry axis. There is a symmetry around, an axial symmetry around this axis. This axis is also called the figure axis. So around this so-called figure axis, you have axial symmetry. And due to the symmetry, this symmetry axis, this figure axis, will also be one of the principal axes. The fact that the top is free means, as in the case of the free rotation around the principal axis that we had discussed last week, it means that there is no external moment of force acting on the top. This is zero, and as a consequence, the angular momentum of the top is conserved. And symmetric means, in particular, so symmetry around this figure axis spanned by basis vector E3 prime. Symmetry implies that two of the three eigenvalues of the moment of inertia are equal. So the eigenvalues 1 and 2, the first two eigenvalues of the moment of inertia are equal. But let's assume that the top is not totally symmetric, and that therefore the third eigenvalue is different from the other two. The dynamics of such a free symmetric top is again governed by the Euler equations. Let us simply look them up and copy them to this current page. These were the Euler equations, and again, they will be the starting point for the discussion of the dynamics of a free symmetric top. Let us see if we can simplify the Euler equations with the help of the assumptions that we made, namely that the top is free and that it is symmetric. First of all, the assumption that the top is free implies that there is no moment of force, and the right-hand sides of these three equations are all zero. Secondly, we assumed symmetry. So as a result, two of the three eigenvalues are equal, theta 2 and theta 1, the two eigenvalues of the moment of inertia are equal, and therefore this difference is equal to 0. So this term vanishes. And finally, wherever we have theta 2, we can replace it by theta 1. So in the first equation, here we have a theta 2, we can replace that by theta 1. And in the second equation, we have here a theta 2, and we can replace that by theta 1. These are the simplifications that we can immediately make due to the assumptions that we have. Now we can rewrite these equations in a compact form. The first equation we can divide by theta 1, and then the first equation reads omega 1 prime dot minus a capital omega times omega 2 prime is equal to 0. Let me, however, start, before I write down the second equation as well, let me jump to the third equation. The third equation simply reads omega 3 prime dot is equal to 0, because the term with the difference theta 2 minus theta 1, that vanishes because of symmetry. The right-hand side is 0. So all that remains is theta 3 times omega 3 prime dot is equal to 0. And therefore omega 3 prime dot itself is equal to 0. And hence omega 3 prime must be a constant, must be constant in time. So the consequence of the third equation is immediately that omega 3 prime is a constant, and I'd like to call that constant omega naught, and this is constant in time. Now let's come back to the first equation that I just wrote. I obtained the first equation by dividing the original equation by theta 1. And the capital omega that I wrote is an abbreviation for theta 1 minus theta 3. So it's changed the order of the eigenvalues, that's why I get a minus sign in front of the capital omega, divided by theta 1. And then I incorporated also the omega 3 prime into the definition of capital omega, of which I know that it's a constant, that it's equal to omega naught. So let me write this with omega naught. And this capital omega is also constant in time, because the eigenvalues are constant in time, and as we just found out, the omega 3 prime is also constant in time. So this is the first equation. The second equation can be reformulated in the same fashion. I simply divide the equation by theta 1, and I find omega 2 prime dot, and then the only difference is that I have a plus sign here, plus capital omega 1 prime is equal to 0. So already the Euler equations look a lot simpler now. Let me try to indicate that in the drawing that I have up here. These are the basis vectors, as before. Then we have a constant angular momentum. And the angular momentum is going to point in some direction. Let me say it's pointing upwards. There's some vector here, capital L. That's the angular momentum, and that is constant in time. And then there is an angular velocity vector, and that points in yet another direction in general. let me indicate it here. Let's say the angular velocity vector omega points in that direction. The red vector, the angular momentum, is constant in time, but both the angular velocity vector omega and the basis vector E3 prime are generally time dependent. So these two here, omega and E3 primed, they are generally time dependent. What we just found out, however, is that the component omega 3 prime is constant in time. What is that geometrically in this figure? Omega 3 primed, that's the component of omega along the E3 prime direction. So that is when we project the omega vector, when we project that orthogonally onto the figure axis, then this is omega 3 prime. And this is again, this is a constant. So whereas the vector omega, the entire vector is generally not constant but varies in time, its projection onto the figure axis is a constant. From this point onwards, let's see if from the equations of motion we can distill other interesting consequences. We can learn other interesting facts about the motion of the free symmetric top. I claim that whereas the vectors omega and E3 prime generally move, they vary in time, at all times the three vectors L, angular momentum, omega, angular velocity, and E3 prime, which spans the figure axis, at all times these three vectors lie in one plane. And I would like to show you, I would like to derive from the equation of motion that this is true. To see that, let's look at the following expression. It's a triple scalar product. It's the triple scalar product of basis vector E3 prime, omega, and angular momentum L. You know that three vectors lie in a plane if and only if their triple scalar product vanishes. So if we succeed in showing that this triple scalar product is zero, then we have proven that they must lie in a plane. The angular momentum is related to the angular velocity by means of the moment of inertia. It's that linear operator theta acting on omega. We can expand the angular velocity in the body fixed frame. We can write omega as the sum over j, component omega j prime, basis vector eg prime. Likewise for the omega, the second omega that we have in this equation. And then we have the operator theta acting on that. But we said that we choose the basis, the body fixed frame, such that the basis vectors are eigenvectors of the moment of inertia. So theta acting on a basis vector, E prime, gives eigenvalue times that basis vector. And hence theta acting on omega gives, I have a different summation index now, sum over k, theta k, omega k prime, ek prime. So we can take all the numbers in front, the components, omega j, and the eigenvalues, and then we have a vector product, basis vector ej, with basis vector ek. And that's something that we had looked at last week. The vector product of two basis vectors of an orthonormal basis can be written with the help of the Levi-Civita symbol. Ej cross Ek equals sum over I epsilon ijk Ei. So together this gives, we have then three sums, sum over I jk, Levi-Civita symbol I epsilon ijk, theta k, omega j prime, omega k prime, and basis vector Ei primed. Now this whole expression in blue still has to be multiplied with a scalar product, taking the scalar product taken with E3 primed. So then we have a scalar product of E3 primed with Ei primed. This scalar product, since it's an orthonormal basis, is equal to 1 if I is equal to 3. And it's 0 otherwise. So in our summation over I, we have a non-vanishing contribution only when I is equal to 3. Therefore, there remain only two summations over j and k, and the I we replace by 3. So we have epsilon 3jk, theta k, omega j prime, omega k primed. In this sum, we learned last week that the Levi-Civita symbol is non-zero only if all three indices are different. So one index is now given, it's a 3. There are only two possibilities where the symbol is non-zero. Either j is 1 and k is 2, or j is 2 and k is 1. In both cases, the product omega j prime, omega k prime gives omega 1 prime, omega 2 prime. The difference is in the theta k, in one case it's theta 2, and in the other case it's theta 3. And these two cases also differ by a sign. So this gives theta 2 minus theta 1, omega 1 prime, omega 2 primed. But theta 2 equals theta 1. The two eigenvalues are equal because we assumed symmetry. This is equal to 0 by symmetry. And hence, this is equal to 0. The triple scalar product of these three vectors is 0. And this implies that omega, L, and E3 prime indeed always lie in one plane. Let's look at further consequences that we can learn from the equation of motion. Let us look at how the angular velocity vector omega changes in time. We already know that it's the component omega 3 prime that is constant, but beyond that we don't know if and how the vector omega changes in time. Now, by definition, omega can be expanded in the body fixed frame, so sum over I, omega I prime, Ei prime. When we take the time derivative of that, then by product rule we get two contributions. We get a sum and then the time derivative of the component times basis vector plus another sum where we have the component and the time derivative of the basis vector. When we look at the first sum, we know that the third component doesn't change. So in fact the sum effectively only ranges from I equal 1 to I equal 2. And then for omega 1 prime dot and omega 2 prime dot, we can insert the equation of motion from the previous page. And we can express that as, so the omega 1 prime dot, that's capital omega, omega 2 primed, times basis vector E1 prime, and the omega 2 prime dot, that is minus capital omega, omega 1 primed, E2 primed. So this comes from this first sum here. As for the second sum, we have omega I prime, and then the change in time, the time derivative of basis vector EI prime, that is, we had that many times before, that is the vector product of omega with EI primed. But then, sum over I, omega I prime, EI prime, this is again omega. So in this second contribution we have omega cross omega, but the vector product of a vector with itself is 0. So in fact this whole term vanishes. As for the term that remains, I'd like to make the following side calculation. We have omega in components, it's omega 1 primed, E1 primed, plus omega 2 prime, E2 prime, plus omega 3 prime, E3 prime. If we now calculate E3 prime vector product with omega, what do we get? We have then E3 prime vector product with E1 prime. This gives E2 prime. So we have an omega 1 prime E2 prime. Then next we will have a vector product of E3 prime with E2 prime. This gives minus E1 primed. Therefore we get minus omega 2 prime E1 primed. And finally we get the vector product of E3 prime with itself, but this vanishes. So this is it. Yeah? So you recognize, when you look at the last line in black, when you can factor out the capital omega, and then you have omega 2 primed E1 primed minus omega 1 primed E2 primed, and this is up to a sign just equal to the E3 prime vector product with omega that I just wrote in gray. So you can write that as minus capital omega E3 prime vector product with omega. What does this imply? The equation says, so omega dot, change in time of the angular velocity vector, equals minus this capital omega, which is constant in time, it's a constant, then the basis vector E3 prime, vector product with omega. This implies that the vector omega is moving on the surface of a cone around E3 prime. And to see that, let's first look at the change in time of the length, the absolute value of the angular velocity vector, or the length of the angular velocity vector, you can write it with the help of a scalar product. It's the square root of omega scalar product omega. The derivative of that is 1 over 2 times the square root. And then you have the time derivative of omega scalar product omega. This gives omega dot times omega plus omega scalar product omega dot. So together it's 2 times omega dot omega. Let me write this down. This is 1 over the square root of omega scalar product omega. And then you have omega scalar product omega dot. That's how the length or the absolute value of the angular velocity vector changes in time. Let's disregard this 1 over square root. It doesn't change our conclusions. And let's use the result for omega dot. Then what we have here, it's proportional to omega scalar product with E3 primed vector product with omega. This is again a triple scalar product. 2 of the 3 vectors are identical. And whenever 2 of 3 vectors are identical in the triple scalar product, this gives 0. This is equal to 0. So this implies that the absolute value of omega is constant. This implies, when you remember the body here, we have E3 prime spanning the symmetry axis of our top, and we have somewhere the vector omega. We already said that this projection here has constant length. That's the component omega 3 primed. That's constant in time. What we just showed here, as a consequence of this equation for omega dot, is that also the length of omega is constant. This implies that the vector omega, it can vary in time, but at all times it must lie on a cone around the figure axis. Because whenever it lies on a cone, on this cone, this gray cone, imagine any position of omega on this cone. The vector always has the same length, and it always has the same projection on the figure axis. So omega must necessarily lie on a cone around the figure axis. So if it moves at all, if omega changes in time at all, it must move on a cone around E3 primed. So omega moves on a cone around E3 primed. This is conclusion number 2 from the equation of motion. Even more than that, we can also read off from this equation for omega dot, since the capital omega is constant, and the basis vector E3 prime always has length 1, it's a normalized basis vector. This equation for omega dot also implies that if omega moves on the cone around E3 primed, the angular frequency with which it moves around E3 prime is constant in time. So the angular frequency is this capital omega, and this is constant. Let's now look at the motion of the basis vector E3 primed. So let's consider how the figure axis moves and evolves in time. So let's look at E3 prime dot. We know this is omega vector product with E3 prime. Omega we expand in the body fixed, in the basis vectors of the body fixed frame. So this is equal to sum over I, omega I primed, EI prime, vector product with E3 primed. The index I can take only two values, 1 or 2. Because if I is equal to 3, then we have E3 prime vector product with itself, and this vanishes. Right? So, and if I is equal to 1, then we have E1 prime with vector product with E3 primed. This gives minus E2 primed. And if we have I equal to 2, then we get E1 primed. So together we have omega 2 primed E1 primed minus omega 1 primed E2 primed. Let's work on this equation a little bit. What I would like to do is I would like to multiply both terms by theta 1 and then divide by theta 1. And then I would like to exploit the symmetry and say that theta 1 equals theta 2. So in this first term here, I replace theta 1 by theta 2. Now again a little side calculation. Consider the angular momentum L. This is related to the angular velocity via the moment of inertia. So it's the operator theta acting on the angular velocity. In components, we've done this several times before. This is sum over I, theta I eigenvalue, omega I primed, basis vector EI primed. Then consider the vector product of L with E3 primed. If for L you use the sum on the previous line, then if I is equal to 1, you get the vector product E1 prime with E3 prime. This gives minus E2 prime. If you have I equal to 2, you get E2 prime vector product E3 prime gives E1 prime. And if I is equal to 3, then you have E3 prime vector product with itself, and this is 0. So there are only two values for the index I that survive, and you find that this is theta 2 omega 2 primed E1 primed minus theta 1 omega 1 primed E2 primed. And you see this is exactly what we have inside the square bracket. So in fact, what we have here is nothing but 1 over eigenvalue theta 1, and then we have angular momentum L vector product with E3 prime. So just as for the angular velocity vector, we have an equation of motion for E3 prime that has the structure time derivative equals some vector cross E3 prime. So this describes again a rotation, and it's a rotation around the axis spanned by the angular momentum. The angular momentum is constant in time. Also the eigenvalue of theta 1 is constant in time. So it's a motion, it's around the constant angular momentum, and as before we can conclude that E3 prime moves on a cone. So with the same argument as for omega, we can conclude from here that not only does E3 prime have a constant length, that's clear because on an orthonormal basis it always has length 1, but we can also conclude from this equation that the projection of E3 prime onto the angular momentum vector, so onto the axis spanned by the angular momentum, that this is constant in time. So with the same logic as for the angular velocity, we conclude that E3 prime must be on a cone around the angular momentum. It moves on a cone around L. And it does so with a constant angular velocity, angular frequency, and this is L, so the angular momentum divided by theta 1. It's a similar logic as for the angular velocity, that the basis vector E3 prime moves on a cone. It has constant length, that's clear because it's a basis vector, it's normalized. But due to the structure of this equation, it also has constant projection onto the angular momentum axis, and therefore the vector E3 prime must always be on a cone around L. And the frequency with which it rotates around this axis is given by the magnitude of this vector L divided by theta 1. Why is the projection of E3 prime onto the axis spanned by the angular momentum, why is that constant in time? The projection of E3 prime onto L, that is the scalar product of L with E3 prime. L is constant in time, angular momentum is conserved, so you can take the L in front, and you have the scalar product with E3 prime dot. For this, we use the result that we just obtained. That's proportional to L vector product with E3 prime. Again, that's a triple scalar product. Two of the three vectors are identical, and therefore the triple scalar product vanishes. So the projection of E3 prime onto this axis of spanned by angular momentum is constant. Let me indicate that here. We have the basis vector E3 prime. We have the angular momentum vector L. The projection of E3 onto L. This is the scalar product L with E3 primed. This is constant in time. The length of E3 prime is normalized to 1. That's obviously constant in time. Now the only vectors with a given projection onto L and with length 1 lie on this cone around L. So if E3 prime changes in time, it can only move on the surface of that cone. And the equation of motion for E3 prime shows that it does so with a constant angular frequency, which is given by the magnitude of L divided by theta 1. So we've now, on several occasions, we've encountered vectors moving on some cone. Here we'd like to draw a picture that summarizes these findings. And we will encounter a total of 3 different cones. Let me indicate the top, the symmetric top. We have the basis vector E3 primed. We have the angular momentum vector L, which is constant. And we have somewhere the angular velocity vector omega. We said that omega must lie, at all times, omega must lie on a cone around E3 primed. This was our conclusion number 2. This cone carries a special name that's called the body cone. And in the German literature, this is called Polkegel. So omega moves on this body cone around E3 primed. Then we learned that E3 primed lies on a cone around L. So let me draw a large cone here. This is the cone on which E3 lies. This was our conclusion number 3. And this cone has another special name. This is called the precession cone. And the German word for that is Präzessionskegel. So the figure axis precesses around the angular momentum. It's a precession cone. Now the very first conclusion that we had drawn from the equation of motion was that angular momentum, omega, and E3 prime, they all lie in one plane. This implies if E3 is on a cone around L and omega is on a cone around E3 prime, and all 3 vectors L, omega, and E3 prime are in one plane, then the consequence of that is that omega must also lie on a cone around L. So there must be another cone here, this one here, and this is a consequence of 1, 2, 3. All 3 results that we have obtained so far imply a conclusion, a consequence number 4, that omega also lies on a cone around L. And this cone has yet another name. It's called the space cone. And in the German literature, you find the name, this is called Spurkegel. When you are given the plane spanned by these 3 vectors, you are given the projection of omega on E3 prime and the length of omega, these are all constant in time, then this uniquely specifies the location of omega. So when you're given E3 prime, you're given L, then this specifies the plane spanned by E3 prime and L. When you're also given the body cone, then there is a unique intersection of the body cone with this plane, and omega must be situated at that intersection. Well, there are 2 intersections, one on each side, but there's sort of a discrete jump between the 2. If, say, at one point omega is, as I had drawn, between E3 primed and L, then this remains so at all times. And there's a unique intersection between the plane spanned by the three vectors and the body cone. This specifies uniquely the vector omega. And when you look at the projection of omega on L, you see that at all times this projection must be the same. And in combination with the result that the length of omega is always the same. So whenever the length of a vector is constant in time, its projection on a certain axis is constant in time, then you can conclude from that that it must lie on a cone around this axis. In this picture you have three vectors. You have in the middle you have the red vector, that's the angular momentum, that's constant in time. Then you see the symmetric top, and its symmetry axis is spanned by this green vector, a thin green vector. That's the E3 prime. That's the basis vector E3 prime. And then you have the purple vector, which is on the surface of that cone. That's the angular velocity vector. That's the omega. And you see how the omega rotates on the surface of that cone, of the body cone. And you see how the green vector rotates on the precession cone around the angular momentum. And you also see how that's sort of indicated with the shadow that you see, a cone, that's the space cone. It's the cone on which the angular velocity vector rotates around the angular momentum vector. One way to visualize that is that you have the body cone, which is rolling. It's rolling around the space cone, and where the two cones meet, that's where the angular velocity vector is.